Hi everyone. This time this video is primarily made up for exhibition purposes. The prime motto or the primary motive behind this making of video is to get positive feedbacks of what more needs to be included in this website. Again, and would be like focusing on the analysis EDA part of my website rather than the prediction part of my website. And there are few of the features that have like incorporated into the dashboard that I want to share it again. I'll be like restarting it from the beginning, and the video is gonna get distributed into two parts. One, it's going to show how things are major related to a specific earth sciences domain problem. Two, how you can use this video for any sort of data or any type of doing analysis of any kind of data that is in your hand, maybe related to your school work, maybe related to your college work, or some company work where you want to put up some graphs, analyze your data, prepare some results, do some zone-based analysis, all those stuff. So I've divided my video into two parts. One will be related to earth sciences domain, other would be a generic one. Again, this the first part relates to the earth sciences domain, where I will be like telling you what are those features which have been incorporated into it. The first one was the same. If you have a data in your hand and you just want to analyze like what's that data all about, how does it start, or what are the values for it, or some knowledge related to that particular domain or that particular thing, you can see it up. It's similar to a data frame head. You can increase the number of values you want till the depth of till the last depth of the point. I can You can analyze like what values it starts from, what type of value is there, or what sort of features are there in your data type. So this is kind of naive one, but still very informative in type. You will get to know about the column types. You will get to know what's the start values and other things. If you don't want that, you can switch to the column name parts, where you can directly see like what are the columns that are present in your data type. These are the foreign types. Like means there we have here we have like five different types of data points. One is related to DTCO, that is slowness values. Other is GR, HCal, row, TDAP. So in earth sciences, what really happens is like when we analyze GTCO, as I told you before, we don't get the continuous data. There are a few times a gap in it. So we try to predict it using other kinds of data, and these kind of problems can surface up anywhere. But today I'm majorly going to focus on the analytics part of like the exploratory data analytics part of this particular data set. So these are the column names which you can straight away see like what all are present there. Going to the next option, if you want to see the description of the data or gain some information about some descriptive analysis of the data, you have two sub options in your hand. One is with data, means at times you have a feature which has data gaps or null values, NA values. So whether you want to incorporate those while doing those analysis part, to know about the mean, standard deviation, quantile points, maxima, minima, the entire data set, or you want to do it without those NA points or with your clean data sets. So things changes, right? Means if there is a null value has a value of some if it has some integral value rather than putting up as np-nan, then it's gonna change or uh, alter your description of the data, the mean of the data, or the standard deviation of your data. These all things have been incorporated into it. Like without those data gaps, your mean, what would be the mean of different features, standard deviation of different features, but with those data gaps, like how it's going to change, how it is all going to change. Next thing is you can analyze the data gap zones or the points or the depth points where you have those high degree of noise individually. You can get to know how many data gap points are there. Then if you want to get some essential information of those data gap zones, you can tap on this particular link and get to know about it. Like there are 363 points which have been altered by heavy noise. And then what is the caliper value at those points? What is the row value? Row and caliper are like different features. What values of those features are in those zones? Because this helps you know like really uh, if I have a noise in that zone, then what is the density of those particular zones? If I have a noise in that zone, then what is the caliper value of that zone? what is the depth value of that zone? What's the mean depth value of those zones? Is it happening on the surface level? Is it happening on the deep level? All those things can be like analyzed straight away from here. What is the maximum depth till where I can get these noise zones? What is the minimum depth where I can start seeing these noise zones? It helps to a great extent. Then at the very same time, you can come up with seeing distribution plots for those particular zones. It will ask you whether you want to include those noise zones in it, or you just want to analyze the clean zones. If you want to include those noise zones, it will ask you to put a threshold for that noise zones. So here I have a threshold for a noise zone for a particular feature, that is caliper. Caliper reads a value from 0 to 15. So I can change, and I need to analyze these two different values, these two different features, which can also be incorporated as a user input feature. And I want to see that, fine, these are the point where noise is quite heavy, but I want to see if I change my threshold value, how things changes. Red zones represent these points which are noisy in type. So I just want to see how many points are there if I keep putting forward those, keep increasing my caliper. Somebody can be of that thought that I don't want to analyze my noise zones because they are of no use, but I just want to analyze my clean zones. Even that feature has been incorporated. It will ask you whether you want to analyze 2D plots or multi-dimensional plots. If you come up with like I want to analyze 2-dimensional plots, straight away going to ask you choose an option, choose two features that you want to see or that you want to describe. Let's choose something like density and velocity. DTCO is the slowness, that's the inverse of velocity, and density we have it right here. I'll put forward like some graph, some scatter plot of this kind. Whatever these points represent the data points in it. These represent different density values. This represents different DTCO values. You can see the variation in both. You can see the variation in row. You can see there are some noise zones at the top of at the means so those rock types which have got higher densities are more noisy in nature. Those things can be like seen from this graph, but it's pretty generic kind of feature where you can include any type of options, any combination of two different features that you want to include into it. Maybe like you wish to see how density changes with depth. Even that can be done. Like with different depths, we can see that at surface zones we have higher density points, which is very rare. Still, at surface zones you have like higher density points, but as you go deep, the density is somewhat constant, or it's lower when it's compared to the surface points. At least it's very rare. Then you say, though, I don't want to analyze only two features at a time. I want to go with three features at a time. That part has been included in this too. You can come up with different multi-dimensional data. It will straight away ask you to put the XYZ features that you want to incorporate, and even the size feature if you want to put it up as like depth points at lower depth will be like of slower size, at higher depth, deeper depths would be of greater size, color, X, Y, Z are the 5 different features that can be incorporated in scatter plot. But here I have included, let's analyze data covariation with rho, and there's one of the spectroscopy data is GR, and you can get to see like yes, this is how your G for different values of GRs. GR is gamma ray. Your DT covariates or DT varies in this way. Or to include, let's say that you want to see how DT change or velocity changes with different values of depth at different with different values of densities at different depth points. So you can do that too. You can see that DTCO is like slowness is quite low at higher depths. That means higher velocity at deeper depths and lower velocity at surface depths. That's good thing. That's something that goes with the norm. Then there's one more thing. It's something related to that how with the measure depth your rho and DTCO changes. But I want to include my signal to noise factor too. So I say that if I increase my threshold, let's say 7, then these red points indicate that you cannot be using any of the dataset points instead of these green points. Well, the green points are the one which that you can use for prediction points as a prediction points, but the red are the one which you cannot use as a prediction point. So you can set a threshold for your particular feature and see that how your uh, dataset changes. These things have been primarily included in my last video too, but the one which I want to focus on right now are the one related to the correlation plot and the polyplot. Correlation plot is one of the things which shows you that how your features are one or in the other way related to other features. But what's so new about it? Anyone can be like coming up with it and use a simple Seaborn library to create it up. And you can create your own heat maps too. But what's good about this particular website? Why should one surface upon it? Because I have incorporated a quantile correlation feature into it. That says, like if you choose a feature, like let's put me first, let me just switch it off once. This is for the entire data set. This is like for the entire 3000 data sets, how your slowness values is related to your density value. It's negatively correlated. And how it is related to GR value, how is it related to the depth value. But it's for the entire data set. It's kind of a homogeneous correlation kind of thing which you wish to apply on the entire data set. And that should not be done, right? Because if it, even in any sort of data set, there are going to be some zones. There's going to be some classification zones where your one feature is going to behave differently in correlation with other feature as compared to other zones where your that particular feature may behave differently. So that is what I have incorporated. If it makes sounds like if I want to know that I want to divide my data set into, let's say, uh, on basis of depth, in say let's 5 different quantiles, and then I want to see that how my things varies. So I find that the first quantile is going to be the surface ones because what quantile does is like sorts your that particular features up or your entire data set in accordance with that feature, and then it analyzes your 5 different subsets of data. So that's what I have done here. Like I've divided my data set into 5 different zones and then analyze how one feature is related to other. So as you can see here, the slowness is heavily related with GR and highly negatively correlated with density. But that may not be the case with other points. Like here, the correlation value is different with GR, but the correlation value is majorly dependent on density. Same goes for the depth points too. Here is more related to GR, but not to the density part. Here is not in the last depth zones. The slowness value is not at all related to GR. Minus 0.08 somewhere is 0, which says that there is no as such correlation between slowness value and GR, gamma ray values in those zones. So while predicting DTCO in the deep zones, you don't need to incorporate GR factor, or let's say the depth factor too, because it's like very less. The degree of correlation is quite low, so you don't want to incorporate those into it. So these kind of things can be learned out from the graph, and you can get to know like here my prime concern is related to Retico, but you can see for other features too, like in different depth zones, how it is like related to different features. You can analyze that up and then create your own prediction analysis out of it. And this can be done for any feature, right? If I want to, let's say, divide my data set up with respect to, let's say, density. I want to keep my quantiles as just 3. I believe that there are only 3 types of dense material. One, very dense. 2, moderately dense. 3, very less dense, means they're shallow or they're hollow. So you can see like how your DTCO varies with depth for very hollow or less dense kind of things, but how your slowness varies with those material where your density is quite high. This is just an example where you can like just divide your data set into zones and then analyze it with different features rather than just in one shot homogeneously reading your data set out. The other prime feature which I have like, included into it is the polyplot. What polyplot does? At times you have a data set in your hand and you feel like it is not linearly related, but maybe related to with some other degree of polynomial or with other degree of some higher degree of polynomial, some higher degree of variation or non-linearity. How you're gonna justify it by this particular plot of mine? you can come up with two different, let's say, dots, and then you can like select degrees in whatever you want it to. Say we want Ditico and row. Okay. Sorry for the instances. I want to analyze my DTCO part with, let's say, row. I put it up there and then analyze it. Like, let's say, just for a linear equation, how my things changes. So you can see it on graph, but how are you going to quantify it? So we can quantify it using some metrics, right? So I've included my mean square error metrics into it. Like if you're going to plot a linear degree equation for correlating these two different features, then what is the error that you want to extract? So this is particular error, MSE error, which is going to come up when you're only using one degree of equation. Let's see it reduces or not for higher degrees of polynomial. It decreases substantially for 2 degree of polynomial. Maybe it decreases more for different degrees of equation. So this is what I wanted to emphasize on this part. Like even if you feel like, obviously this variation is primarily because of the outlier part, but let's analyze for that reason some other variable too. But here we can see like if your 1 degree of equation is not able to realize the entirety of data, you can use different type or different degree of equations. Somebody can say like, okay, velocity is directly related with density, then why will be using different uh, different degree of equations? That's because there are always non-linearity present with different depths and because of different combination uh, reasons. But I'm not going to get into specification of it. So just let's just analyze a spectroscopy variable with slowness. That's JR versus DTCO. So what happens? What if I plot DTCO versus GR? I only use a simple linear regression to realize this DTCO factor using GR. I get to see that there's high degree of error, MSE error. Even the R square value is going to be quite low because it's not able to realize the entirety of data very well. But if I increase the data set, let's say to some high degree of polynomial, so see that somewhere the error changes and realization improves. And this can be increased to any number you want, let's say 6, or somebody can come up with a random number 15. So it will let you know like is there really a change in MSE values for high degree of polynomial? Is it really improving on your graph, or it's only increasing the complexity of your equation type? All those things can be incorporated alongside. For different zones, different degree of polynomial equations can be used, right? So this is for the entire data set. You can utilize both correlation plot and polyplot at the same time and see whether for different zone, different degree of what degree of equation can be used for realization of two different curves. Now getting to the second part of my data set or my particular video, I wanted to let you guys see like how particularly these things can be used for any data set around the world. Means this is something which is only related to earth sciences data sets, right? But you can use it for other data sets too. How you're gonna do it? So once you land on the website, it's going to ask you to put a file address. A file address is a simple Google link of any of the CSV, XML, Excel file that you have, which can be easily created. I have one here from Geek for Geeks or some website. So I'll be using it for, sorry, so I'll be using it for my analysis. I'll just put up the file address right here and then just print enter. What's going to do is it's going to read the entirety of that data set and then let you know how you're going to analyze it straight away. The steps are same. You can see the preview option, increase the number of data sets you want to see the number of type of columns present in that particular data. It's a generic file, right? You can just extract it up and then analyze it in whatever ways you can. Show me the description of that data. I'll show you the description of that particular data. This is one of the NBA file listing the names of those players. Then you can like get to know that what is the main, how many players are available there, how many players are available, what's the mean age of them, what's the mean weight of them, what's the mean salary of those people. Whatever data is that is available there can be like displayed through. If you want to see that how many players are there whose everything is being mentioned in that particular data set. There are only 364 players who has given their entire information, but in totality we have 457 players. If you analyze those particular players up, you can create their dimensional plots too. Let's say that somebody wants to analyze their BMI. So what they can do is like, or some other feature. It's not like that. It's not that tough kind, but they can put up their weight and their height and creates their own scatter plots at the time and analyze it out. How it is like different? It's different in a way that if you want to, it's different because of those correlation parts and the polyplots, because that's the major thing which I wanted to show up here. This is how the entire dataset correlates, or different features of the datasets in entirety of different features in the entirety of datasets behave with relation to other features. But let's say I want to do a quantile correlation, and I want to divide these NBA players up into three different quantiles with respect to their age, like the one who are young, middle age group, and maybe say the older ones or the veteran ones. So how it is going to change? There are few features which really changes, like their weight factor. In what way it depends on their salary. Like for the new guys, it is not that much correlated, but primarily for the other guys it's correlated in a different way. Or the weight factor, how it is related to age. For the veterans it's not that much related, but for like the young players it is like negatively correlated. Like your weight increases, so your age should go, or as you increase with your age your weight should come down. But if we see that for the veterans, it's a different way around. It's not at all related, or it is like positive related. Other features behave differently too for different dose zones. So this is somewhat one of the prime feature of this particular data set. Other than that, you can all do those things like creating a multi-dimensional plot, um, where you have your, like, let's say age, and then your number, whatever is there, and let's say your weight, and you can create those multi-dimensional plots here too to just analyze that how many number of players do have that particular weight, or what is the age of those players with how age is related to weight. So simple analysis can be done. Other than that, group-based correlation can be performed, and descriptive analysis is a one touch thing now for everyone. Means any sort of data that you have, any school related project, any college related project, descriptive analysis can be done on hand. And at the very same time, you will get an option to even uh, particularly download those things, download these graphs if you want to. But if you want to save those images, you can do it right away. Even I'm going to provide an option for that. So multiple things can be incorporated. So this video is primarily for showcasing my ADA part and for requesting all of you who are watching it to provide me with insight that what more features you want to incorporate into the EDA website of mine. Like what are your demands, what are your requirements, so that I can like put it up for in this particular website of mine. That's a solemn request. I believe that you're going to help me with that. Thank you.